Hello class, you're welcome back. Today we are on chapter 7 and we want to study the quantum mechanical model of the atom. The quantum mechanical model explains how electrons exist and behave in an atom. How electrons exist and behave in an atom or in atoms. So that's what quantum mechanical model explains. So it will help us, this model will help us understand and predict the properties of atoms. Properties of atoms. So that's all the model is to do. And this theory can help us understand why some elements gain electrons while others do not. And it will also help us to understand why some elements are very reactive while others are inert. So that is what this model is going to help us understand. But in order to study an atom, we need to talk a little bit about the nature of light, because in order to get information from an atom, we need to probe it with light, because it's light that can penetrate in it and come out and give us some information. So the nature of light. Light is a form of electromagnetic radiation. It's a form of electromagnetic radiation. Light composed of perpendicular oscillating waves, one for the electric field and the other for the magnetic field. But they travel at constant speed in a vacuum, which is 3.0 times 10 to the 8 meters per second. So this is an electromagnetic radiation. So the red line represents the electric field and the blue line represents the component of the magnetic field. So you see, this is 90 degrees. 90. And this too is moving at 90 degrees. So that's why we say it's perpendicular. So you see, that's how they are moving. But let's look at light. Say it's oscillating waves. So what are waves? Let's look at some characteristics of waves. Characteristics of waves. You say this is a wave, an example of a wave. You have this. These are the peaks. So the distance between two peaks is what we call the wavelength of the wave. The height, you see the height, this is the amplitude. Then down here we have the trough. So this is the characteristic. This is a characteristic of wave. This is how a wave is described, by its wavelength or by its amplitude or by frequency. So frequency is the number of cycles a wave completes in a given period of time. So for example, you have a line. Let's say we have a line here. I'll just give a line here. Let's say we have a line here. And the waves are coming. Give some example of. So we have one here. It crosses the line. Then we have another one. So you see, this one has shorter wavelength, this one has longer wavelength. This one with shorter wavelength will cross this line more. More cycles will cross this line than this one. That's what we mean. So frequency is the number of cycles a wave completes in a given period of time. Units of waves, units of frequency are hertz or cycles per second. A wave that has shorter wavelength will complete many more cycles in 1 second than one that has higher wavelength or longer wavelength. So what does this represent? It means that wavelength and frequency are inversely proportional. We can see the equation here. This is the frequency, this is the wavelength, this is c, that's the speed of light, which is constant. So we are still on relationship between the wavelength and the frequency. For waves traveling at the same speed, the shorter the wavelength, the more frequently they pass through a particular point per second. This means that wavelength and frequency of electromagnetic waves are inversely proportional, as we have said. So, since the speed of light, c, is constant, if we know the wavelength, we can find the frequency, and vice versa, because the speed of light is constant. So we just need to know one of them, the wavelength, then we'll find the frequency, or we know the frequency and we'll find the wavelength. So this is the same equation. This is frequency, this is wavelength, this is speed of light, which is constant. So let's take an example. Red light has a frequency of 4.62 times 10 to the 14 per second. Calculate the wavelength in nanometer. Speed of light is 3.0 times 10 to the 8 meters per second. So that's the frequency, we need the wavelength in nanometers. So we have to move from the frequency to wavelength in meters, then we convert to nanometer. We're going to look at the conversion factors. So we're going to get one conversion factor from this. This is how we convert nanometers to meters. So those are the two conversion factors we need. So these are the conversion factors. Lambda is c over frequency. Then 1 nanometer is equals to divided by 10 to the minus nanometer. So it's equals to 10 to the minus meters. So 1 nanometer is equals to 10 to the minus meters. So we want to find the wavelength, that's the wavelength, c, that is c, frequency, that's frequency was given in the equation. When we do that, you cancel the units, make sure you're working, taking care of the units. And this is what we have as the wavelength in meters. So what we need to do, we need to multiply by this conversion factor to change it to nanometers. So that's what we are doing next. So this is our wavelength in meters. Then this is the conversion factor. So the red light is 6.49 times 10 to the 2 nanometers. Or we can write it 649 nanometers. So that is the wavelength of the red light when you know the frequency. Let's talk about electromagnetic spectrum. So electromagnetic spectrum is a continuum. You see, the frequency is from 10 to the 4th hertz to 10 to the 24 hertz. And in terms of energy, we have the radio, which is the weakest. Then we have the microwave, then we have the infrared, then we have the visible light, then the ultraviolet, the X-ray, then the gamma ray. As you live from left to right, the energy becomes higher. But let's look at visible light. Visible light, when you see it, is white. But when you spread it using a prism, you see these different colors. It starts from red and it ends to purple. We call this the visible spectrum. And it's from 400 nanometer to 750 nanometer in wavelength. So the color of light is determined by its wavelength. White light is a mixture of all the colors of visible light. We call it a spectrum. So that spectrum starts from red, you see the red, it goes to orange, it goes to yellow, it goes to green, it goes to blue, then violet. You can see it here. That's it. When an object absorbs some of the wavelengths of white light while reflecting others, it appears colored. The observed color is predominantly the colors reflected. So the color we see are actually the color reflected, not the ones that it has absorbed. When an object absorbs some of the light. So let's talk about how waves interact, how they interact with one another. When waves are in phase, you see, we call this constructive interference. You see, these two are in phase, you see they become very large. When they interact, they become large. We call this constructive. But when they are out of phase, you see, they're out of phase. This is destructive interference. You see, it becomes a flat line. There's no wave again, see. But here, you see, it became bigger. Here is a flat line. The wave is destroyed. After we have talked about how waves interact, let's look at a term, diffraction. When traveling waves encounter an obstacle or opening in a barrier that is about the same size as the wavelength, they bend around it. Take note, wavelength, you see waves go like this. So we are talking about this point to this point. That's the wavelength. So if there is an opening, and this opening is about the length from here to here, that's what we are talking about. It's a barrier that is about the same size as the wavelength. So we are comparing this wavelength to this opening. That's what we are talking about. They bend around it. This is called diffraction. So when traveling waves encounter an obstacle or opening in a barrier that is about the same size as the wavelength, they bend around it. This is called diffraction. The diffraction of light through two slits separated by a distance comparable to the wavelength results in an interference pattern of a diffracted waves. So the diffraction of light through two slits separated by a distance comparable to the wavelength results in an interference pattern of the diffracted waves. So let's look at this. Let's look at diffraction. For a wave, you see, we are looking at the wavelength. This is the wave. Let's assume that the wave is moving. If the wavelength is equal to this slit, of course, it's going to go through, and we call this diffraction. For particles, of course, these are particles, they just move. The one that goes through the hole, they just pass through. So this is how particles behave, but this is how waves behave. So we want to look at two slits and how the interference is. So we have light and we have these openings here. Here you see this opening is half the length of the wavelength. Look at this. So when it comes out, it will not be in phase. So the interference of the waves here will be destructive. And see, you have this. It becomes flat, so you have this dark place. But in this case, this blue, the slit is just equal to the wavelength. Equal to the wavelength. So it comes out, you see, it's a bright light. It passes. It may form a constructive wave. But here is destructive. So here is destructive. It turns into a flat line. Because the wavelength, the distance is half the length of the wavelength. So here the light becomes brighter, but here is dark. Here is brighter because it's constructive. You see, it's more, it becomes bigger. After we have talked about interference of waves, let's look at photoelectric effect. Photoelectric effect. It was observed that many metals emit electrons when light shines on their surface. So many metals were observed to give up electrons when light shines on their surface. It means there was some interaction between the electrons and the light. And we call this photoelectric effect. So according to this theory, if the wavelength of light is made shorter, the light waves intensity made stronger, more electrons should be ejected. More electrons should be ejected. So in experiments with photoelectric effect, it was observed that there was a maximum wavelength for electrons to be emitted. And this maximum wavelength is called the threshold frequency, regardless of the intensity. Regardless of the intensity. So if that wavelength does not meet this maximum threshold frequency, electrons will not be emitted. Electrons will not come out of the metal. So it was also observed that shorter wavelengths light with dim source cause electron emission without any lag of time. The source was dim, but the wavelength was short. So, Einstein's explanation about this photoelectric effect. Einstein proposed that the light energy was delivered to an atom in a packet or in packets. So in packets. And he called this packet a quantum or a photon. So that is how this light was emitted. That is why it did not depend, it depends only on the energy of the light. So the energy of a photon of light was directly proportional to its frequency and inversely proportional to its wavelength. Energy of the photon. So the proportionality constant is called a Planck's constant, which is H, and has the value 6.626 times 10 to the minus 34 joules times second. So this is a relationship between the energy of the light and the frequency. And we know frequency is related to the wavelength. So if you want to find the energy of the light with respect to frequency, you use this, but you can use the wavelength too. Let's take an example. Calculate the number of photons in a laser pulse with wavelength 337 nanometer and total energy of 3.83 millimeters joules. So this is our wavelength in nanometer. This is our pulse in millimeters joules. So what we need to do, we want to find, we want the number of photons. So we need to find the energy of the photon. So number of photons. So we have to come from the wavelength in nanometer, convert it to meters. Don't find the energy of one photon. Don't find the number of photons. So we need to find the energy of a photon. So this is our equation to find energy. This is our conversion factor, nanometer and meter. This is our conversion factor of millimeters and joules. Then this is our equation to find, we use to find the energy of a photon. So from this relationship, we are going to get the conversion factors. We'll put the conversion factors here. So those are the conversion factors that we are going to use for our calculation. So we want to first by changing our nanometers to meters. So that's what we'll do first. So we have 337 nanometers. We want to convert it to meters. So that's our conversion factor. So the wavelength in meters is 3.37 times 10 to the minus 7. This is wavelength. This is wavelength. It's a wavelength. So from wavelength, we have it now in meters. Let's find the energy of the photon. So our E photon is Planck constant times the speed of light in a vacuum all over the wavelength. So with this calculation, we can get the energy of the photon. So that's the energy of the photon. So this is our Planck constant. Take care of the units. So the units cancel meters. So we are left with joules. That is joules. So the energy of the photon is 5.8985 times 10 to the minus 19 joules. So now we want to find the number of photons. So we are going to divide the total energy by the energy of the photon to get the number of photons that gave us this total energy. So that's what we are doing. So number of photons is, so we are converting our energy first to joules, because our energy, we have to convert the total energy to joules, because the energy we have for the photon is in joules. So we use this conversion factor, and we know that we have 3.83 times 10 to the minus 3 joules. So now the number of photons that we have is 3.83 times 10 to the minus 3 over 5.8985 times 10 to the minus 19 joules, which is the energy of one photon. So in total, the number of photons that gave us that energy is 6.49 times 10 to the 15 photons. So that is what gave us the total energy, 6.49 times 10 to the 15 photons. So we've been able to calculate the energy and the number of photons. Now we want to look at ejected electrons, the energy related with ejected electrons. So ejected electrons, one photon at the threshold frequency gives the electron just enough energy for it to escape from the atom. And that energy, we call it the binding energy. That's how we call it, the binding energy. So when irradiated with a photon with a shorter wavelength, it means it has more energy. The electron absorbs more energy than is necessary to escape. So when this atom is irradiated, you send radiation to it, which has shorter wavelength, more energy. The electron will absorb more energy than is necessary. So this excess energy becomes kinetic energy of ejecting the electron out of the atom. So kinetic energy is energy of the photon minus the binding energy. So this is kinetic energy, energy of the photon minus the binding energy. So we can write it this way. And you know, energy of the photon is Planck's constant times the frequency. So we have talked about ejected electrons and the energy associated with it. Let's talk about spectra. When atoms or molecules absorb energy, the total energy is often released as light energy. In nature, we see that fireworks, neon light, mercury light, sodium light, hydrogen light, we see it as light. Most of the time, we see the colors. So when that emitted light is passed through a prism, a pattern of particular wavelengths of light is seen. That is unique to that type of atom or molecule. The pattern is called an emission spectrum or spectrum of that particular atom or molecule. And most of the time, this pattern is unique for that atom or molecule. It doesn't change because it describes its internal structure, that structure that is associated just with that atom or molecule. And because of that, it can be used to identify the material. It's used to identify the material. So we'll look at some spectra. So emission spectra, you see, look like this. This is for hydrogen. You see, when the light comes out of hydrogen, you see, it breaks into 1, 2, 3, 4. And look at them, you see the lines. Every other thing is dark because hydrogen atom did not absorb it. And this is for hydrogen. Anytime you do this for hydrogen, these are the wavelengths you will see. Because it has to do with the internal nature of the hydrogen. This is the helium spectrum, and this is that for barium. But look at white light. White light does not have black spot. It's a continuum. It's a continuum. So these lights which are being absorbed are absorbed by the element. And you see, it is specific of this particular element. Hydrogen has its own. Helium has its own. Barium has its own. So we can use this spectrum to identify these elements. So let's analyze these spectrums a little bit more. So Rydberg analyzed the spectrum of hydrogen and found that it could be described with an equation that involves inverse square of integers. That's what he realized. And the equation is for lambda 1 over lambda, this is wavelength, equals 1.097 times 10 to the 7 per meters multiplied by 1 over m squared minus 1 over n squared. So this is his equation. But I want us to go a little back on Rutherford's model, Rutherford's nuclei model of atoms. Rutherford said that atoms contain tiny dense center called nucleus, and the electrons move around in the empty space of the atom surrounding the nucleus. But what is the limitation of this model? The nuclear model of the atom does not explain what structural changes occur when atoms gains or lose energy. It didn't tell us that. So nuclear model of the atom does not explain what structural changes occur when the atom gains or loses electrons. So on this note, Bohr decided to come up with an explanation. Bohr developed a model of atom to explain how the structural atom changes when it undergoes energy transition. So Bohr's major idea was that energy of the atom is quantized. It enters the atom in the form of a package, and that the amount of energy in the atom is related to its electron position. It's related to the position in which the electron is in the atom. So quantized means atom can only have very specific amounts of energy. They can have only very specific amount of energy. So the electrons travel in orbit that are at a fixed distance from the nucleus. So that is why these atoms or these electrons can absorb only fixed amount of energy, because this distance in which the electrons are fixed. That is what Bohr said. So when they absorb this energy, that's when they change to another fixed position. So that's why when they give up this energy, they give a fixed amount of energy. So electrons emit radiation when they jump from an orbit with higher energy down to an orbit with lower energy. Take note, they are fixed position. The emitted radiation is a photon of light. So let's look at Bohr's model. So this is an example of Bohr's model and emission spectrum. So we are looking at hydrogen. This is what he came up with hydrogen. So this is the nucleus of the atom, the hydrogen atom. This is n equals to 1 level. We'll talk about it, what this means. This is n equals to 2. This is n equals to 3. These are the positions in which the electrons can reside. That is Bohr's explanation. That they are stationary, this position are stationary. So when an electron leaves from a higher energy level to a lower energy, it gives out light in the form of a wavelength. And this white light falls in the visible region of the spectrum. It has a particular wavelength, and that's why you can see a particular color. Then when a second electron, another electron, or this same electron moves from here to here, it gives out this light that has this wavelength, which comes out as blue. Then when it moves from n equals to 3 to n equals to 2, it gives out light, which is associated with this wavelength and which is red. So this is Bohr's model of to try to explain why elements can emit only specific wavelengths of light when they absorb energy. So Bohr looked at an electron as a particle, which is a particle. But let's continue. Let's talk about waves. Wave behavior of electrons. De Broglie proposed that particles could have a wave-like character. And why did this was needed? Why did de Broglie come up with this explanation? It's because Bohr's calculation, mathematical calculation, did not help explain with atoms that have multiple electrons. So they had to find out why. Why is it that for hydrogen, this calculation is perfect? Or for an atom that has just one electron, this calculation was perfect. But when you have multiple electrons, it did not work. So de Broglie came up to try to explain why this will not work. So he said particles could have wave-like character also, even though they are particles, but they can have wave-like characters. So de Broglie predicted that the wavelength of a particle is inversely proportional to its momentum, mass times velocity. Because it is so small, the wave character of electron is significant because it is very small. So the equation for wave in relation to its wavelength is in relation to a momentum was given like this. Planck's constant divided by mass times velocity. So let's take an example. So let's look at that calculation, that equation I used it to calculate. Calculate the wavelength of an electron. This is the mass traveling at 2.65 times 10 to the 6 meters per second. So this is the velocity. Take note, this is velocity, not frequency. Velocity. This is the mass. And we want the wavelength in meters. So we are moving from the mass and the velocity to give us the wavelength in meters. So this is our equation. So when we substitute, this is our Planck's constant. J is our Planck's constant. This is Planck's constant. Then this is the mass, and this is the frequency. The velocity, not frequency. So with that, so the wavelength is 2.74 times 10 to the 10 meters. Okay, class, we will continue next class with this. So next class we'll talk about the uncertainty principle of the uncertainty principle. That's what we'll talk about next class. So thank you till we meet again next class.